Hello guys, we are from Group 5. We will explain about Spline.
Okay.
Uh, our member is A Satrio, Thomi Akbar, and Zaenal Arifin. Spline. In computer graphic, a spline is a curve that connects two or more specific points, or that is defined by two or more points. The term can also refer to the mathematical equation that defines such a curve. Consider the set of points in the illustration below. It is easy to envision a curve or red that approximately connect the 4 points blue. In the old days of mechanical drafting, a flexible metal or wooden strip called a spline, and the term from which the present term device was used construct approximate graph such as this. A computer can be used to test various curves, having known formulas for an optimal fit for any finite set of points. The example shows here a near perfect fit exists, and the curve has a relatively simple formula. Not all splines are this straightforward, but in theory, at least one spline curve can be found that approximates a continuous graph for an infinite set of points. The Bezier curve, produced by the Bernstein basis function, has limited flexibility. First, the number of spatial polygon vertices fix the order of the resulting polynomial which define the curve. The second limiting characteristic is that the value of the blending function is non-zero for all parameter values over the entire curve. The B-spline basis contains the Bernstein basis as the special case. The B-spline basis is non-global.
Properties of B-spline curve. B-spline curves have the following properties, which is the sum of the B-spline basis function for any parameter value is 1. Each basis function is positive or 0 for all parameter values. Each basis function has precisely one maximum value except for k equals 1. The maximum order of the curve is equal to the number of vertices of defining polygon. The degree of B-spline polynomial is independent on the number of vertices of defining polygon. B-spline allows the local control over the curved surface because each vertex affects the set of a curve only over a range of parameter values where its associated basis function is non-zero. The curve exhibits the variation diminishing property. The curve generally follows the shape of defining polygon. Any affine transformation can be applied to the curve by applying it to the vertex of defining polygon. The curve lies within the convex hull of its defining polygon. Bezier curves. Bezier curves is discovered by the French engineer Pierre Bezier. Bezier curves can be generated under the control of other points. Approximate tangents by using control points are used to generate curve. Properties of Bezier curves. Bezier curves have the following properties. First, they generally follow the shape of the control polygon, which consists of the segment joining the control points. They always pass through the first and last control points. They are contained in the convex hull of their defining control points. The degree of the polynomial defining the curved segment is one less than the number of defining polygon points. Therefore, For four control points, the degree of the polynomial is 3. An example is cubic polynomial. A Bezier curve generally follows the shape of the defining polygon. The direction of the tangent vector at the endpoints is same as that of the vector determined by first and last segment. The convex hull property for a Bezier curve ensures that the polynomial smoothly follows the control points. No straight line intersects a Bezier curve more times than it intersects its control polygon. They are invariant under an affine transformation. Bezier curves exhibit global control means moving a control point alters the shape of the whole curve. A given Bezier curve can be subdivided at a point t equals t0 into two Bezier segments which join together at the point corresponding to the parameter value t equal t